Welcome to the third lecture of this series of lectures on one variable calculus. In the last two lectures we had learned quite a bit about numbers. We have spoken about rational numbers and irrational numbers. We have spoken about the union which we call real numbers. We have also shown that the rational numbers are countable and real numbers are uncountable, and hence the set of irrational numbers are uncountable. But it will be interesting to, because they are so abundant, the irrational numbers, it will be interesting to see that we should be able to show that some number is irrational. Rational numbers are easy to detect, because if you have a number in the form p by q, it is rational. But how do you know which number is irrational? Irrational numbers are not in the form p by q, it is not so easy to detect. So, the detecting a numbers irrationality is an interesting exercise, and I think it is not very bad, and it will bad idea, and it will show the inner connections between two different parts of mathematics. It will show how theory of equations are used to actually tell you which number is irrational. We have already mentioned in the first lecture about numbers that one of the most well known irrational number is that called root 2, and this is the example that is given in your classes in higher secondary also, that this comes out of a geometrical fact which simply comes out of the Pythagorean theorem, that if you have a right angle triangle with say 1 centimeter side each, then this should be also the hypotenuse should be of length root 2, and this cannot be expressed as a rational number. These are called incommensurable quantities by the Greeks. So, now when you look into this, how do you prove it? So, proof is again using the method of contradiction, in the sense that if I want to prove that it is irrational, I consider that it is rational and I take it in the form p by q, and then show there is some, I have goofed up somewhere, there is some contradiction. So, this is a very proof by contradiction is one of the biggest tools the mathematician has, and he uses it repeatedly everywhere. So, what we do now, next we square it, and that would simply imply that p square is 2q square. So, 2q square is a number divisible by 2, any number, even number is divisible by 2. So, what we do is the following, we immediately understand that p square is an even number. So, what does it imply? It implies that p is even. So, if square of a number is even, then the number must also be even. So, if p is even, we can write p as twice of some quantity m. So, because any even number can be written as 2 of m, where m is some number, because p is, or if it is the even number, it is always divided by 2. So, p must be expressed as twice of some number. So, that is m is the quotient when you divide p by 2. Now, what you do is you put back here. See, one important assumption that we take when we express the thing in the form p by q, that we are expressing in the most reduced term, that is here in this case you have the greatest common divisor between p and q as 1, they are relatively prime actually. That is, you cannot make any further cancellations to reduce their levels. I mean, it is not 2 by 4. If it is 2, we should write it as, we should never write as 2 by 4, it is should write it as half. It is called the most reduced form of a rational number. So, there is no common factor between them other than 1. So, if p is 2m, I will put here in this equation p square equal to 2q square, to get 4m square is equal to 2q square, which simply would give me that q square is 2m square, which would imply that q square is even. So, it implies that q is even. So, if p and q are both even numbers, which means 2 is a common factor, means 2 divides both P and Q, right. So, it cannot happen because here I have considered P and Q in the reduced forms. So, they do not have any other common factor other than 1. So, here we reach a contradiction and hence we conclude that this is irrational. Now, I will ask you the following question, and nobody asks, and this is given in the beautiful book of Niven. Niven has this beautiful book which I think it's not available nowadays, it's not also always available on the net. It's called Numbers, Rational and Irrational. It's published by the Mathematical Association of America. Niven was an old Canadian American mathematician. In the 50s, I think he was very active, and he has some lovely books which everybody should read, actually, anybody interested in mathematics, because he shows how beautiful mathematics can be. So, we will follow his chapter on irrational numbers for this lecture. So, he asks a question, what about root 3? Is it rational or irrational? Is this irrational? That is the question. So, in your school you are never asked this question, even in your standard calculus courses you never ask the question, why should root 3 be irrational. Now, let me again try in the same way. So, I again assume that root 3 is equal to P by Q. You will be given the notes would be uploaded and then you can see it in detail. So, I am not writing everything, every word in detail or the way I have written in the notes. So, what does it mean? So, I am expressing this again, P by Q must be in the reduced form, that is, you will always assume that this GCD, the greatest common divisor between P and Q is 1. So, this would imply that 3 Q square is equal to P square. So, what it simply means that P is divisible by 3, P square is divisible by 3, not sorry P. So, it simply means P square is divisible by 3. So, P square is divisible by 3. But an interesting fact that if the square of a number is divisible by 3, the number itself also has to be divisible by 3. This is a the number theory consists of all these fun and tricky facts, and you really have to use it whenever required. So, it implies P is divisible by 3. So, that implies that P can be expressed as 3 times some K, say. This is divisible by 3, 3 is the quotient when you divide P by 3. So, if I put this in this equation, so you will have 9 K square is 3 Q square. So, that would imply that Q square is 3 K square, which implies that Q square is divisible by 3. And hence it would imply that Q is divisible by 3. So, now 3 becomes a common factor between P and Q, which is not possible because we have said that P and Q, the only common factor P and Q has is 1. So, again just if you want to keep in mind, this is in the reduced form. Okay. Now, Niven asks you another question. What would happen if I add these two numbers, will they be rational or irrational? Because you might say, oh, you are adding two irrational numbers, you will get an irrational number. Beware, adding two irrational numbers need not always give me an irrational number, because if you have root 2, then without much difficulty using the same procedure you can prove that minus root 2 is also irrational. So, but then root 2 plus minus root 2 would give you 0, which is the rational number. If you take two rational numbers and add them, or if you take two rational numbers and multiply them, you will always get a rational number, but you cannot guarantee that such a thing would happen when you have two irrational numbers. So, the question is this rational or irrational? So, shall we go here? The policy of doing this, when you add two numbers, the policy of doing check of rationality or irrationality in this form is not always helpful. That is, you cannot say I can put root 3 by thing as p by q and do it, it will mess up. The policy of doing this, as I will show you on this side of the board, is the following. Now, if I assume that it to be rational, so let root 2 plus root 3 be equal to r, rational number. If I square it, so this is what you get, or in another way you get root 6 is r square minus 5 by 6. So, you add 2 plus 3 and that is taken to the other side and divide by 2. Now, if I divide, when you say, so r, if it is a rational number, r square minus 5 is a rational number. Now, if you divide two rational numbers, they will give me another rational number. Then the question would arise, is root 6 a rational number? If root 6 is a rational number, then okay, what I am writing is true. So, if you want to prove it irrational, you have to prove that root 6 is irrational, and that is exactly what I want you to prove. You can keep on thinking about this. So, how would you prove that root 6 is irrational? So, if you want to, so when you are proving just a single quantity, then you have to go in this p by q method with p by q in the reduced form. So, just for your practice, we will just do this example. So, again you will go, because if you prove that root 6 is irrational, then this is a meaningless equation, right, a rational cannot be equal to irrational. So, then you will immediately conclude that root 2 plus root 3 is not rational. Somebody say, okay, I know that it will be rational because it is nothing but root 2 into root 3. But remember, multiplying two irrational numbers need not be again an irrational number, because again you have root 2 and exactly in the similar procedure you can prove that 1 by root 2 is irrational. Only the role of p and q switches, right. So, then when you take a product of this, you will get 1 which is rational. So, these are certain things you have to keep in mind while doing mathematics. So, again if you do in the form p by q, so you will have 6 q square is equal to p square. Which means p square is even naturally, because it is 2 into 3 q square. So, p is divisible by 2. So, p square is even. So, it implies p is even. So, now p is even, I can write p as 2 of m. I can write p as p equal to 2 of m. So, this is clear now, because that is the type of reasoning that we are taking. So, once you do that, you write 6q square is 4 4m square. So, you are getting 3q square is 2m square. So, what does it mean? It means that 3q square is even. Now, if 3q square is even, q square itself must be even because 3 is odd. If you want to multiply an odd number with some number and get an even number, so if you multiply an odd number with odd number, you would never get a even number. To multiply an odd number with an even number, you will get an even number. So you will immediately have from here as that q square is even, and which will imply q is even. So, both p and q being even now would have a common factor of 2, which is again a contradiction, because as you know that p and q has been chosen in the reduced form. All these things that we have done, these are the parts you will learn in your 11th standard in our Indian classrooms. They are called shards. Go to any class 11 book, you will be hearing this word shards. So, in general, the question that I would be interested to ask is the following: is it always easy to show such numbers to be irrational? It is not always easy. These examples are, though it is not also a traditional, these examples are not traditionally given in the classrooms. But for example, I am asking the question, when can this nth root of a, when is this number irrational? The answer is surprisingly interesting. The answer is the following. The answer is that nth root of a is either an integer or irrational. Of course, a is a positive number, naturally we are not talking about root of a negative number here. So, a possibly is an integer. So, when is this a irrational number? So, the interesting thing is that this is either an integer or irrational. It is never in the fractional form. So, that is a very interesting question, but how do you actually prove that? A can be integer means how?
Square root is
nth root, but yeah, you can take integer, because if you take the square root, then there will be a problem, because you cannot take you take the fourth root, there will be a problem. So, because we want to have real numbers, we are generating real numbers, we are not generating anything else.
If you know minus 8 to the power 1 by 3, then 3 roots will be there.
Exactly. Now, observe that if I look at this number, I can look at this number and say, okay, this is something you have done in your complex number theory, that xn minus a is equal to 0 has one real solution at least. So, nth root of a is a real solution of this polynomial equation. So, the question would be, will this solution, will this polynomial equation, because I can write it as a solution, real solution of this equation, can it give me some hint about the irrationality of the number or rationality of the number, or be it an integer. So, to do that, we need to know something about the properties of numbers, properties of solutions of polynomial equations. And whatever we do, we will not do the proof here, it will be there in the notes. Everything is based on a very single thing, unique factorization theorem for natural numbers. That is the key to all these things that we are discussing, and that shows the unity of mathematics in some sense. So, now look at this thing, consider a polynomial equation. So, what I am going to write down is a polynomial equation, and you have seen all these things when you talk about the theory of equations, and many of you must be knowing, but this is what is called a polynomial in a single real variable. So, polynomial of degree n. So, the power progressively goes down to C1 x to the power 1 plus C0, and Cn is not equal to 0, because if Cn is 0, then it becomes a polynomial of degree n minus 1. It is a polynomial of degree n. Look at the following polynomial equation, and these numbers C1, Cn minus 1, C1, C0, these are called coefficients. Okay. These coefficients, we for the time being take them to be integers. You can always replace integers by rational numbers. I will ask you to have fun by checking why you can do so. It will be really fun just if you go through it, but the interesting fact is that we can now look at certain properties of rational solutions of this. Suppose we have a polynomial equation, that is, and you know that such an equation will have at most, it will have exactly n solutions, not at most, it will have exactly n solutions, right. So, these C0, C1, Cn are integers. I am not giving you the proof, I am just stating a result. The result says that if A by B, here I am just talking about a rational number where A and B could be negative, positive, does not matter, or if you want to say P by Q, if P by Q is a rational solution of the above equation, then P divides C0 and Q divides Cn. But this all comes from a very simple result, this all comes from prime factorization. P divides C0 and Q divides Cn. So, from which we can make a very interesting conclusion that if Cn is equal to 1, then Q must also be 1, which means, because otherwise if it is 1, there is no other number other than 1, no other integer which can divide 1. So, 1 or minus 1, it does not matter. So, subasuming the sign of P, Q in P, then you will have P by 1, and so this is an integer. So, if Cn is equal to 1, P by Q is element of the set of integers. So, this is a very important result. To prove this, you need some stuff which is in the notes, which I will not get it to you in the class, because we are obviously constrained with our time. So, we have some maybe 5-10 minutes left. So, here is something you have a information that if it is rational, then there is a behavior, P behaves in some way and Q behaves in some way if you have a rational solution. Now let me ask you this question, cube root of 5 is irrational. Can you prove it? And you will see how beautifully we can use this idea. This simple idea can be beautifully used here, because I can now write that this is a solution of the equation of the polynomial equation of degree 3 x a cube minus 5 is equal to 0. So, in this case C0 is 5 and C1 is Cn is 1, means C3 is 1, rest of the coefficients are 0. So, suppose root 5 is cube root of 5, which is the real solution of this. Suppose cube root of 5 is rational, then it must be an integer, because Cn is 1, C3 is 1, the highest power has coefficient 1. So, it must be integer. So, actually and then cube root of 5 is an integer. Then what could be the integers, but that integer now should divide C0, which is 5, because P is dividing C0 and Q is dividing Cn. See how beautiful mathematics is. And then you know the only chances here are 5, minus 5, 1 and minus 1. So, now I put x as say 1, say 1 cube minus 5, it is obviously not 0, it is minus 4. Similarly, you will look for each and everything here, every solution. If you put x as 5 or minus 5, 1 and minus 1, you will not get 0. So, cube root of 5 cannot be a rational number. So, you see how the theory of equations are linked to finding rational number, irrationality of numbers of this form. So, once you have, so you can use the same language here, that either it is an integer, fine. If it is not an integer, there is no other choice, but it has to be rational, it cannot be of the form p by q. Now, you might ask that okay, only this square root type, cube root or nth root type things are irrational, nothing else. No, there are famous numbers in mathematics, famous constants in mathematics which are irrational. The most famous constant in mathematics is pi, the ratio between the circumference and the diameter of a circle is irrational. Not only that, pi square is irrational. So, this is irrational. And there is another important number called e, and the square of e, the exponential, that is e is actually 1 plus 1 by 1 factorial plus 1 by 2, 1 plus 1 by 2 factorial plus 1 by 3 factorial and so on and so on. So, it is it's a infinite series. Okay, if you are not so much into it, do not bother much about it. So, in my notes I will have proofs of the irrationality of these numbers and say something more about them, but these are for somebody who has already got some knowledge. So, the notes would be so that people can choose and read whatever parts they want to read. So, before we finish today, in the last 5 minutes, let me give you another important class of numbers, logarithms. Many of the logarithms are irrational actually. Now, I will not talk about base e logarithms, which is called natural log. We will call the straight the class 10 standard logarithm, which is as follows. So, you know that if 10 to the power x is equal to y, so if I ask the question what is the power of x, what is the, to which power 10 must be raised to give me the number y. So, log is just the inverse of this operation, inverse of exponentiation is the log operation. So, you say log to base 10 of y is your x. Now, I ask you a very simple question. If you look at Napier's logarithmic table, they will give you point something something, but that will be just a approximation. No, I am asking, is this rational or irrational? Okay, let me assume that it is rational as before, and the whole thing is in the reduced form. Say A by B in the reduced form, GCD is 1. Greatest common divisor between A and B is 1, that is you can't divide them further, there is no common factor other than 1. So, it means B to the power log 10 of 2 is A, which simply means log 10 of 2B is equal to A, and that simply means 10 to the power A is 2 to the power B, and hence it implies that 2 to the power B is 2 to the power A into 5 to the power A. So, 2 to the power B is some number. And this looks like this is a prime factorization then of 2 to the power B, which has got to be unique. And each of the prime numbers in the prime factorization must be a factor of this number 2 to the power B, right. Each of these numbers here must divide this number 2 to the power B, but 2 to the power B cannot be divided by 5. So, here comes the contradiction, and hence this is an irrational number. So, with this I end this talk. I hope you enjoyed this with some nice examples, and you will see more in the notes, especially those parts are for those who are more initiated, calculus for the ambitious. This is a name of a book recently by T.W. Corner, calculus for the ambitious. So, those who are more ambitious can go and have a look there in the notes, but otherwise those who just want to have a basic idea about how to go and hit irrational numbers, this amount of knowledge is pretty fine to develop a working knowledge of the calculus. Thank you very much.